So we're going to find and understand cross product of two geometric vectors and the cross product of two algebraic vectors and understand the three basic properties of cross products. So here is a bit of a blurb about that. So we've talked about dot products before, sometimes called a scalar product, because remember that when you take a dot product, you don't get another vector, right? So you take two vectors and you dot them, what you get is a number, right? So it's usually referred to as a scalar product. But we're going to look at the cross product today, and this is sometimes referred to as a vector product because what you get from crossing two vectors is another vector, or a third vector. And he made the point that this vector is a vector. If you think of two, remember what we call them position vectors. Position vectors are vectors that go from the origin out to some point in space, whether in two space or three space. This stuff that we're doing, cross products, only relates to three space. He made that point before. You don't have cross products in two space. You have dot products in two space and three space, but you don't have cross products in two space, only in three space. Because what happens is that when you cross two vectors, so if you look at these two vectors here, and I'm pointing to it on the screen right now, the A and the B vector, when you cross them, right, so think of these as position vectors again, going from the origin out to some point in three space. When you cross them, A times B or B times A, what you end up with is a vector which is at right angles to each of the vectors that you cross. So it's the A times B vector, A cross B vector is at right angles to the B vector and at right angles also to the A vector, sometimes referred to as being orthogonal. I used that word too yesterday, something that's at right angles, or something that's what's called the normal. I've used the term normal with you before, which means that something is at right angles. If you either hear the term normal or the term orthogonal, it means the same thing. All right, so the cross product of two vectors A and B is denoted by A times B, not dot. So you don't see a dot this time, you see a cross, right? And it's equal to A times B, the magnitude of A times the magnitude of B, times the sine of the angle between them, where theta is the angle between them, and n is the unit vector. So there is a unit vector perpendicular to the plane. So perpendicular to perpendicular means at right angles to the plane of of A and B, right? So unit vector, of course, means it has a distance of 1. And really what this is telling is that this part of it here, in fact, let me just circle it. This part here represents the magnitude of that vector, right? And you're scaling that unit vector, which has a magnitude of 1, scaling it by multiplying it by that scalar. Right, so that's the magnitude. This part that I just circled is the magnitude of the A times B vector. Okay, so when it creates what we call a right-handed system. Now, I know he showed you that on the video a few minutes ago as to whether your thumb points up or points down, and where if you're curling towards one. Don't pay a lot of attention to that. Just know that the order in which you multiply two vectors does matter, because multiplying it one way, so if I did A times B and I got a result, then the B times A, and this is going to come up in a few minutes, the B times A is just going to be negative of the original result. So if you had an answer for A times B and you wanted to get B times A, you didn't want to go through that long process, just take all the numbers in the original vector that you got, the cross product, and just change your sign, and you get the new vector. Right? So that's what this all means. That's the scalar part. That's the magnitude of the vector in the box. And then the n is just simply the vector that is running either up or down, depending on how you multiply these two vectors. And that's the unit vector, but that's scale because of this magnitude right here. Okay? All right, so there you go. That's the sort of basic definition. Now, if vector v is x, y, z, and vector A is A1, A2, B2, sorry, A1, A2, A3, and B is B1, B2, B3, then A cross with B, right? Then it means that it also suggests that if the two vectors are at right angles to each other, the V vector is what you're going to get from multiplying the A times the B, right? It's perpendicular to the V, right? The V vector that you create, and it's also perpendicular to the A. I just made that point a while ago, which also means that the dot product of those two vectors will be equal to 0, right? So the cross product gives you a vector which is perpendicular to both the original vectors A and the vector B, but it also means that if I were to take A times that, what the result of the cross product is, if I multiply the A vector times the result, I get z, and that's multiplied in terms of a dot product, that is, that I would get 0. Because remember that when you dot two vectors that are at right angles to each other, I should get 0. So that's all the point that this is making here is. All right. Now, shortcut for find the algebraic cross products. I'm going to go through what he just did, and then I'm going to show you what I consider to be the better way to do it. So this is the way to get it for algebraic vectors. Write the components in separate columns, right? He did it going across, I think, but I'm going to do it in columns. So it's 3, 4 minus 2, that's one vector. And the other vector is minus 2, 2, 5. And I want to find A times B. So you don't use the first two numbers. So you don't take the 3 and the minus 2, which comes from the x component of both vectors. So you start with the 4, then you go to the minus 2, then you cycle back to the 3 and the 4. So that's kind of what he did, but he did it going across. Then you take the 4 times the 5 and minus the minus 2 times the 2. That's what this is saying here. Eventually going to get 24 minus 11 and 14. Now, if you want to spend some time doing that, be my guest. But here is what, and you know, I have no issue with you choosing the method that works best for you. And maybe I should spend more time on this because I don't want to dismiss it as being somehow inferior. So it's so remember now, you don't put the first number in when you start off, right? You start off with the 4, then you go to the minus 2, then you go back to the minus 2. So that's why it's 4 minus 2, and then you go back to the 3, then you go back to the 4, and so on and so forth, right? The second column is from the B vector, so you do the same thing. You're going to go 2, which is the second number, then you go to 5, then you go back to minus 2, and then you go to 2, and so on and so forth. So if you really, really want to go through that, then I think the best thing to do is come and see me and we can work through that. Let me show you what I think is the better way to do it. So I want to multiply the A vector times the B vector. And it's the same ones that we just did on the previous page. Of course, we're going to get the same answer. We're expecting to get this answer right here. But here's what I think is better. I'm going to take, you see what I have up here? I, J, and K. I'm going to create a little table. I'm going to put I, J, and K here. Then I'm going to put the numbers that come from the first vector, 3, 4, and minus 2. And the second vector, minus 2, 2, and 5. Now, I want to get the first number that comes out of the cross product. So here's what I do. I'm going to use a dotted line for this. Let's just get a good dotted line here. Dotted line, line. Hold on for me, please, folks. Here we go. Okay, here we go. Dotted line. Actually, no. I'll use a line. And I'll use red. So I want to get the I column, all right? The number that comes from the I. So what I'm going to do is I'm going to put a line through here and put a line through here, right? So I'm in a sense crossing out the I, all right? And then what I'm going to do now is I'm going to take these 4 and create my first number. And the way this works is, so it is kind of in a sense similar to what he did, but not quite. I'm going to take the 4 times the 5, so the 4 times the 5, and minus the minus 2 times the 2. The minus 2 times the 2. Right? So I'm taking this and I'm minusing that. Hopefully that makes sense. So in the first case, I'm going to get 20. This is going to become 4. So it's minus 2 times 2 is minus 4. So you're minusing minus 4, which is plus 4. So the first number is 24, which is exactly what they got in the first one. So there's a 24 that I just got from doing that. Right? So here's what I did. To get that, I put a line down through the I column and put a line that goes across the top. I'm going to leave the line that goes across the top exactly where it is because that's always going to be there. Right? But my first number is 24. Now, I'm going to go ahead and take away this line. Actually, I'm going to move this line over. That's what I'm going to move this line over. And then I need to erase, actually, let me do another thing here. Let me erase, you know what, I should have used, all right, I need to erase this thing right here. All right, I'm just gonna erase all of this and put them back. And if I use lines, I can just move the lines. Okay, so it was 3, 4, minus 2, and minus 2, 2, and 5. So what I'm going to do, and remember what I did, I took the 4 times the 5, and then I minus the 2 times the minus 2. That's how I got that 24. I'm going to move that line over now because I want to get to the J column. All right. So I'm going to come over here now and take this. Oh, sorry. I'm going to take this line and move it over here. Then I'm going to do the same thing again. There's one little quirk to it, which I'm going to explain in a minute. I'm going to do the same thing. So when I put that line through them, I'm not going to use those numbers that I put the line through. So I'm going to go with now 3 times 5 minus, so 3 times 5 minus 2 times minus 2. Okay, minus 2 times minus 2. So 3 times 5 obviously is 15. This is minus 2, that's times minus 2, which is 4. So I'm minusing 4, which of course is equal to 13. Now, here's the one little quirk to it, which unfortunately you just have to memorize. If you go back and look at what we have as the answer over here, you notice that it, oh, minus 11, I did something wrong here. I don't know why 15 minus 4 turns out to be 13. It never was, it never will be. So let me fix that. Nobody said anything to me. So it's actually 11. But what you'll notice is that the answer for the cross product is actually minus 11. So it means that the little quirk to it, which, you know, if you can just get past that, is still going to make your life a lot easier, is just change the sign of what you get from the middle cross product. Okay? So if this turns out to be 11, then really just make it minus 11. That's all. All right? That's the only quirk to it. I'm going to go through now and find the last one. So I'm going to move my line over again. Right? So it's actually not 11, but minus 11. Right? But I'm going to do the same thing I did for the last line. So I'm going to move this over. There we go. So now I'm blocking out this column for the K. So how do I get my K now? My K would be 3 times 2 minus 4 times minus 2. Okay, so 3 times 2 minus 4 times minus 2. So 3 times 2 is 6. 4 times minus 2 is minus 8. So it's minus minus 8, which of course is plus 8. And that answer is obviously 14. So let's just double check over here. Hopefully I didn't screw up again this time. No, it's actually 14. So the result of all of that is that my cross product, so if it was negative, we change. Yeah, oh, yeah, thanks, Aaron. That's a great question. If it was negative, we change it to positive. We just simply change the sign of the middle one. That's the only thing that's kind of a little bit that you just have to remember. Right? Just change the sign of the middle one. Okay, so my answer for this is we had 24. The cross product of these two is 24 minus 11 and 14. Right? I personally like that method a lot better than the one that he did. No disrespect, Mr. Richards. He's a great online instructor, but I much prefer this method 24 minus 11 and 14. Okay, so it's your turn now. I'm going to start you off. I'm going to see if you can get the answer for this one. Right? So I'm going to set up a little table. There's my I, there's my J, there's my K, and I'm going to put the numbers, remember it's A times B that we're doing. So I'm going to put the 4 minus 5 and 0 in the top column. And I'm going to put the 9 minus 3 and minus 1 in the second column. So I'm going to leave this for you in just a minute, but I'm just going to remind you that the first thing you need to do is put a line through the top. Let me take this line here and copy it for you, or clone it for you. All right, so let's take this and put this right here. So that's the starting point. And then I'm going to clone this line as well. And this one I'm going to start off here. Right, so I'm going to do the very first one for you. Then I'm going to leave you to finish up the rest. Right, so the very first one, the very first number for the I is going to be the -5 multiplied by -1 minus the -3 times the 0. Well, that's actually easy, right? Because that's just 0. So the first number is actually going to be 5. So that's my first component, right? I'm going to ask you now to do the rest. Do the J component, shift the line over by 1, then do the K component. All right, everybody, try that, see how that works out for you now, please, everybody. I want to intimidate anybody, so why don't I take a volunteer on this one? Who thinks they have the 3 components of the cross product of this vector? Kushi, go for it. So -4, you say it's J. Okay. Not commenting yet. I'm just asking for your answer. And what about the K? I'm looking for everything now. 33. Okay. What do other people think about Kushi's answer? Is she 100% right, 50% right? Same, but +4. Got the same, except you got the +4. Flip the J. Yes, you got to remember that. So Kushi, you're on the right track, okay? But you got to remember that you got to flip or change the sign of the J. So whatever you get, you just simply change that sign. Instead of putting it as a positive, it becomes a negative, or a negative becomes a positive. Okay, does that make sense, Kushi? So you're very, very close. Okay, now here's what we should do just to prove this, that this is actually right. One of the ways that we can prove that this is in fact and I'm going to write that down, by the way. So 5 -4 and 33, right? That is in fact, sorry, 4, +4, +4. I wrote down what Kushi had. Let me fix it. We just get rid of that. So 5, 4, and 33 is the cross product. Now, there's a test, right? So we're going to see in the 4 minutes that we have if we can pass that test. If I multiply this vector, the 5, 4, 33, by one of the original vectors, so let's say the 9, dot it. I shouldn't say cross. I should have said multiply by a dot product. By the 9, -3, and -1, if I dot those two vectors, right? So we did we did dot yesterday. What I'm asking now, if I were to dot, I'm lost. How did we get the 33? Okay. Okay, let me backtrack and sort of help Ariana with that. So for Ariana, for the last one, for the 33, what I'm going to do is I'm going to take my line, I'm going to move it over here. Okay? So here's my diagonal. My diagonal is 4 times -3, right? Make sense? Is minus what? 12, I guess. I'm going to add to that the 9. Sorry, minus from that. I got that wrong. It's minus. You're not adding. I'm thinking about the dot product right now. We're going to minus from that. Let me undo that last part. So -12 minus, so it's 9 times -45. Okay, but you put, oh, it's a 9. I put, is my writing that bad? Is that what is Aaron, are you trying to tell me that my writing is so horrible that you thought my 9 was a 6? Is that what you're saying? Okay, anyway. So yeah, so that's how we got it. Okay. All right. All right. Anyway, so let me erase all of that. And I know we're running up against the clock here, folks. So let's just quickly get this done. What should you expect if I dotted these two vectors right now, right? The 5, 4, 33, which is the cross product of the first two vectors. What if I were to dot that with the 9 minus 3 minus 1? So one of the original vectors. What should you expect to get from that result? Dotting it, not crossing it, but dotting it. And dotting, of course, is very easy. What should I expect to get by dotting these two vectors? Anybody? Can anybody tell me what you should expect to get by dotting it? Nobody knows what the result of this should be. I kind of mentioned it earlier on, though. Get 0, yes, you should. Because remember that what you're getting is a line, a vector, shouldn't call it a line, a vector, which should be at right angles to both of the pre-existing vectors. Well, let's see if that's actually true. So the dot product of the dot product, no, not the cross product, the dot product of this should be 5 times 9 plus 4 times minus 3 plus 33 times minus 1. Well, 9 fives are 45 minus 12 minus 33. Guess what, folks? That's actually equal to 0. Right? The same is true. The same is true if I were to multiply, and it should be, the 5, 4, 33 by the other vector that we were crossing it with, the 4 minus 5, 0, if I dot it. All right, so I'm dotting it now. So 5 times 4 plus 4 times minus 5. Well, the last part is just going to be 33 times 0, which of course is just going to be nothing. 5 times 4 is, what is that, 20, and then minus 20, which again is equal to 0. All right, we'll take a break for 5 minutes. Remember, it's a 5-minute break, and we'll come back and we will continue with our work on cross product. So I want to hopefully make sure everybody's clear on why, when I multiply the resulting cross product with one of the original vectors as a dot product, when I say multiply, it's not cross multiplication, it is dot multiplication, that I got 0. Remember, let me take you back a page here. I want to make sure everybody's clear on this. If I take you back a page to, let's see if I can find the diagram here. Right? These two lines here represent lines that are, we're taking the cross product of them. They're like in a plane. And we have a line that is at right angles to both of them, mutually perpendicular to both A and B. So if I took a dot product between B and this resulting vector, I should get 0. Because one of the things we learned yesterday is that the dot product of two perpendicular vectors is 0. So that's why I'm getting 0 from both. It's perpendicular to both A and B is what we're saying. Okay, so let me move forward now. Now, determine the magnitude of A cross with B. So remember that one of the definitions of geometric vectors for magnitude, right? So this is what we're trying to get. The magnitude of it is equal to the magnitude of the individual vectors, which is the 3, multiplied by the 5, but multiplied by the sine of the angle between them. Okay, so 3 times 5 times the sine of the angle between them. So let's get those calculator fingers working. I think it's time for me to introduce the wheel as you're doing that, by the way. The wheel kind of needs to always be part of our lives because it's the way we kind of keep everybody honest here. It's always very fair as to who it chooses. Hang on, wheel of names. Here we go. Give me a second here to bring up your class. MCV, here we go. And so when I call on you from time to time randomly from whatever the wheel selects, it's not, don't take it personally, folks. It's just a way that I can sort of keep everybody on track and engaged in everything. So I'm going to be asking Jessica to give us what the result of that multiplication is. It's very simple multiplication. I'm just multiplying 3 things together. Jessica, what are you getting for that magnitude? Give me 2 decimal places, please, Jessica. Jessica, check in first for me, please. Let me know you're there. And then tell us what that result is. Go ahead, Jessica. Okay, thanks. What's the magnitude of the cross product of A and B? If the length of A is 3, the length of B is 5, and the angle between them is 40 degrees. So what would the magnitude of that resulting cross product be? What do you say to that? So you have your calculator handy there. 9.6. Okay, I'm going to take that as being correct. I don't hear anybody else objecting. So I'm going to assume that nobody objecting means that you got it right. Okay, if anybody is not sure about that, it's a very simple formula. It's just a formula, right? If I want the magnitude of a cross product, I just take the magnitudes of each of the vectors and multiply by the sine of the angle between them. Done. Now, let's get a little bit more practice with this. P is equal to 1 minus 2, 4, and Q is equal to 3, 2 minus 2. Find P times Q. It says also Q times P. Well, don't do that yet. What conclusion can you infer about the commutative property for cross products? So all I need everybody to do now, and yes, I'm going to call on one of you, not voluntarily, but I'm going to be calling on one of you for the answer for that. I'll ask each person for one component. So I'm not going to draw the little table for you. I'm going to invite you to draw that table for yourself, right? Put these, now you're multiplying P times Q. So the P vector goes on top and the Q vector goes second, right? If you were multiplying Q times P, which is what the second part of the question is asking you, then you put the Q vector first and then the P vector. What I want you to do is put the P vector on the top line and the Q vector on the second line. So I'm not going to draw that table for you, right? So I'm going to give you a couple of minutes, and then I'm going to be calling on 3 people it's now 11:27, in a few minutes to give me each of those components of the P times Q, P crossed with Q, right? That's what we're asking for. And I'm expecting 3 answers from that, an X, a Y, and a Z. By the way, thank you, Jessica. Okay, so I'm going to start off with Ashvan. Ashvan, check in for me, please, first. Let me know you're there, Ashvan. Perfect. Ashvan, can you give us the X component of the cross product of these two? So you're getting -4. Let me get some feedback from the rest of the class. Does -4 work for you as well? Okay, Alexander, Tomileo, Vanessa, Carly, Sarah, Taj. Excellent, excellent. Okay, good, good. And I agree, by the way, -4 is correct. Okay. All right. Thank you very much, Ashvan. Good stuff. Taking you out for now. All right. So I'm going to accept the answer not as 10, but as 14. And Ella, I'm going to suggest that you try going through that again. Okay. So that was Ella. And I have one more person I need to ask for an answer. And that honor goes to Anika. Anika, check in first for me, please. And please give me the last digit that you got by doing the cross product of those two vectors, the P vector and the Q vector. Go for it. Let me hear what you got. So you're getting 8, you're saying. Okay, well, what do other people think? Does that answer make sense? Alexander is saying yes, Kushi, Adam, Carly, Ashfan, yes, and I'm going to agree with that answer. I would absolutely agree with that answer. So the P times Q is the -4, 14, and 8. That's true. That's true. But let me ask you now, without actually doing the calculation, Javier, thank you. Without actually doing the calculation, what should I have for the Q cross with P vector, right? Can anybody give me what that answer is? You just flip the signs. Thank you, Richard, because it's really the vector running in the opposite direction. It's like multiplying this vector by a scalar of -1. So you know you're showing that right-hand rule thing. This vector will be going up, the other vector will be going down. So it would be 4, -14, and -8. That's all. All right, just flip the signs, like what Richard said. Right? Whatever was positive becomes negative, and what was negative becomes positive. It's as simple as that, because it is essentially a vector running in the other direction. Okay, let's move along. Okay, now here's an important, let me make this bigger because I know the writing on this looks a little small. let's just talk about whether any of these things are actually possible. It says state whether each of the following expressions is going to give me a vector, a scalar, or is not even defined. It can't be done. All right? So let's think this through very carefully now. What should I get from going through this process? If I took a u vector and dotted it, excuse me, with a v vector times a w vector, am I going to get a vector, a scalar, or neither one? What do you think, folks? I'll throw this out to the class, right? You should know what you get when you multiply various things. So take it in stages. Do what's in the brackets first, right? Try to use a BEDMAS principle. And you tell me what you think your final answer is. So I'm not asking for a number. Okay, let me just be clear. I'm not asking for the number to be 6 or 9 or components. I'm not asking for that. I'm asking for what should the nature of the result be. Is it a vector, a scalar, or it cannot even be done? So Adam is thinking that, no, again, I'm not asking for a number. So you're thinking 0. I don't know whether it's 0 or anything. I just want to know if it's a vector, a scalar, or it's none of this. So Adam is thinking it's a vector. What do other people think? I'm dotting U with the product of V and W. And the product of V and W is a cross product. So does everybody agree with Adam that the result of this is a vector? What does everybody else think? Come on, folks, I need to get some reaction from you. How do you know? Well, we're gonna reason it out, right? That's what I'm asking you to do. We need to reason it out. Does anybody okay, so Kushi and Adam are on the same page, right? Kushi is on the Adam bus right now, thinking that this is a vector. Does anybody think it's a scalar? Or does anybody think it can't even be done? Sarah is not even going to go near that bus. She's saying, no, this is a scalar vector if it's a cross product. Interesting. So I've got more people saying vector. Only one person is saying scalar, and there's nobody thinking that it can't even be done. I'd like to get a little more reaction to that. I want you to think it through. Let's think this through. Figure out. Let me give you a little bit of a hint because you're asking me how do we know, Fernando? Do the stuff in the brackets first and ask yourself what results from that, right? Take that result and then do the other operation that's outside of the bracket and then ask yourself, what is the answer? Vector if it's a cross. Okay. So what is the answer, right? What is the result of all of this, right? I've only seen a few people responding. I want to know what other people think, right? I just want you sitting here looking at the screen. I want you to think this through for yourself before I sort of give away answers here. All right, let me ask a couple of people directly then. All right, let me do that. Let me ask Richard. Richard, what do you think? You think it could be a scalar? Richard, what do you think? Taj is now sort of going on the Sarah bus here. All right, Richard, chime in for me, please. What do you think? I say it's probably a vector. Interesting. So most of you think it's a vector. By the way, nobody's thinking that it can't be done. Excuse me. Well, let's take it in stages. Let's take it in stages. Let's do this part first. The stuff in the brackets. Brackets tend to be the first thing that you want to do. When you multiply using cross multiplication, when you cross it, right? When you do the cross product between a vector and a vector, what do you get? Get a vector. Perfect. When you take a vector and dot it with another vector, what do you get from multiplying, from dotting two vectors? So you're right. I'm going to get a vector from this. That's a vector result. I'm going to take that vector and dot it with another vector. So it's vector dot vector. You get a scalar. That's exactly right. So Sarah, big up to you. Right? You're the first one who said, I think it was Sarah said it. Yes, first one who said it was a scalar. And absolutely it is a scalar. right? When you dot two vectors together, you get a scalar, right? It's called scalar multiplication. A cross product is a vector multiplication. Two vectors that are cross multiplied by crossing them, give you another vector. But that vector times another vector in a dot multiplication gives you a scalar. So the result of this is a scalar. Okay, so maybe the first one people didn't quite understand what the question was. So let's get to the next one. How about u dotted with v crossed with m crossed with n? Vector, scalar, or not even possible? What do you say? Okay, again, I'm waiting for you to tell me, folks. I'm not giving away the answer right now. All right, I need people actively engaged in thinking this through. So I'm getting vector, getting vector. Okay. Any other answer? So vector. Okay, Kashaf. Okay, Alexander. Okay, Thomas. Okay, Fernando. Right. Okay, Taj. Everybody says vector. Okay. Is there any other answer? Does anybody think it's a scalar? Does anybody think it can be done? Right? Are all gonna stick with vector? Yes, no, maybe so. Okay. Let's work through this. When I dot, let's go to the first bracket. When I dot u with v, what do I get from that? The first part. Let me just focus on the first part, right? When I dot those two, I get a scalar. Perfect. So I'm going to get a scalar here. What do I get? And I circle with another one. What do I get when I multiply by a cross with a vector with another vector? So m times n is being crossed. I get a vector. So the question is, take a scalar and multiply it by a cross with a vector. It can't be done. Thank you, Sarah. It can't be done. You can't cross a scalar with a vector. If you're going to cross anything, it has to be another vector, right? You cannot cross a scalar with anything. You can cross a vector with a vector, but you can't cross a scalar with a vector, right? You can't cross a scalar with a scalar. They're just numbers, right? To be able to cross anything, you need a vector. So it can't be done. Not possible. Everybody understands that. I want to make sure that I'm not sort of flying through this and people aren't clear on that. It cannot be done, right? How can you multiply a number using a cross multiplication of a vector? Think of how we just did crossing two vectors, right? Where we needed to have an x, y, and a z component. If one of them is just a number, how is it going to be possible? Can't be done. Okay, so unfortunately, we're batting, apart from Zara, we're batting 0 for 2 right now. Let's see if we can get the last one. So I'm crossing u with v. I'm taking that result and I'm crossing that with w. All right? What are people thinking this time? Okay, so we're back on the vector bus apparently. All right? Okay, vector didn't work out so well the last time. A lot of people were going with vector, didn't quite work out, but we're back on the vector bus. All right, and we're sticking with it. Everybody's jumping in with vector. Is there any other answer? Is there anybody who's thinking this is not even possible? Or is anybody thinking I'm going to get a scalar? Right? What do other people think? All right, let me see if I can call on a couple of people here. Okay. Danny, what do you think? Are you thinking vector, scalar, or not possible? Danny, check in for me, please. Let me hear from you. What are you thinking? A lot of people are saying vector, but what say you? What are you thinking? You're thinking vector. So all of you think is vector, eh? Interesting. Well, the answer is, yeah, it is a vector. Okay, let me not hold that in suspense anymore. If I take a u and a v, if I take these two and multiply them, I can cross two vectors and end up with a vector, right? And then that vector is being multiplied by another vector in a cross when I'm crossing them. And yes, I can cross two vectors, and the result of that is in fact a vector. So no problem there whatsoever. You draw that was not that was not my goal. All right, that was not my goal. Anyway, so that third one is a vector. So the first one was a scalar, right? Because you're multiplying, you're dotting. The first part gives you a vector when you cross these two, but when you dot that with another vector, you end up with a scalar because the product of a dot is a scalar, right? The product of a cross is another vector, right? But you can't take a scalar and cross it with a vector. And then the final one is you can multiply two vectors and you get another vector. All right? Okay. If anybody isn't clear on that, we can certainly spend more time on it. Let's move on though. Given A is 345 and B is 202, verify that A, the magnitude of A times B does indeed equal A magnitude times B magnitude times the sine of theta, excuse me, where it's an angle between 0 and 180, and the angle is between is between 0 and 180. All right. So we're about to try this now, and this is going to give us some good practice with how this works. Now remember this. This is the definition. Let me put a little thing around it. This is the definition of a cross product for geometric vectors. It's the magnitude of A times the magnitude of B times the sine of the angle between them, where the angle between them is between 0 and 180. And we can also, and these are algebraic vectors here, and we can cross those quite easily and find its magnitude. So this is the magnitude for algebraic vectors. This is the magnitude for geometric vectors. But are they equal? We're going to go through that process right now. So here's your task, right? Your task, first of all, is to go ahead and find the cross. So we're going to do this first. We're going to find the cross product between A and B. I'm going to turn it over. This is more practice for you. Now I'm going to call on three people in a minute. And then after we find the cross product between them, we're going to find its magnitude. And we know how to find magnitude when we're hitting the cross product. So go ahead now and find a cross between these two vectors. All right, I'm going to give you a few minutes to do that. And I'm going to go to my wheel in the meantime. Last person was Anika. Thank you, Anika. I'm taking you out for now. Yes. Mm-hmm. Yep. Sure. 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 In fact, the question that I gave you on, I'm going to give you on the test is going to use, in fact, if you remember that thing we're doing yesterday with tug of war, I did use north, 25 east and all that other stuff. So that's, yes, you absolutely can expect that to be the case. Yes, you can use that. All right. All right. No problem. All right. So, folks, you're all, and I have a name right now, and I'm not giving that name away yet. I need you all to go ahead and find the cross between 345 and 202. And once we have that cross product, we're going to find the magnitude of that cross product. And we're going to compare that to the magnitude using the other formula for cross products, okay? Which is the length of A times the length of B times the sine of the angle between those two vectors. All right? So I'll give you just a minute now. I think you should be good at this. So I don't think you should need a lot of time to get that cross product anymore. And I have my name lined up, ready to go. All right, I said I couldn't give you as much time as the last time, so clocks run out, folks. It's Stephen. Check in for me, please. Let me hear from you. Just first of all, just check in, and then we're going to ask you for what that cross product is. All right, Stephen. Let me get just the first part of that cross product, please. So it has three components. what is the first component of that cross product? The x component, in other words. First one is 8. And everybody else, what do you say? Are you all going to agree with Stephen on that one? Is 8 the first number? Okay, all right. Okay, good, good, good. Talea, Fernando, Jordan, Alexander, you got a lot of people, and I'm going to say you're right, and Carly as well. Okay. All right, that was Stephen. Thank you, Stephen. I'm looking for the middle number. Don't put it in the chat, please. Just wait. I'm looking for the middle number to come from Vanessa. Vanessa, let me hear from you first, please. Want to know you're there. Great. Oh, okay, then. I was just asking for you to check in, but okay, you got your number. And I'm just going to go ahead and put the 4 in because the 4 is right. Okay, so you don't need to agree. I'm just going to put the 4 in. That's good to go. Thank you, Vanessa. And then finally, let me remove Vanessa and ask for the third number from Kushi. Kushi, check in for me, please. Let me know you're there. And then if you could give me -8. Excellent. Okay, so this represents the cross product between A and B. So this is A crossed with B. But what I'm really interested in is the magnitude of that. So I need the magnitude of this vector. So I'm going to remind you that the magnitude is equal to the square root of the squares of all of these numbers. So 8 squared plus 4 squared plus -8 squared. And without taking a lot of time on that, that works out to be the square root of, sorry, help me out, please. Could you tell me what that works out to be very quickly? 8 squared plus 4 squared plus -8 squared. Anybody quickly? 144, thank you. Oh, I think I remember this question now. And that's easy, that's 12. Okay, so this is the magnitude of these two vectors. But what if it was the other way that we find that magnitude, right? So the square root of 144, of course, is 12. And thank you, Carly and Richard and Jordan, by the way. So good, we know what the magnitude of that is now. But let's try to do this the other way. It says A times B sine of theta. Uh-oh, sine of theta. We don't have theta. We don't have the angle between these two vectors. So we're kind of stuck here. Is there something we learned yesterday that would help us to find the angle between two vectors? Does anybody remember this from yesterday? The angle between two vectors. I have the two vectors, 3, 4, 5, and 2, 0, 2. Is there a way that we can find the angle between two vectors? Well, this was yesterday, folks. 24 hours ago. Please don't tell me you forgot this already. You remember us finding the angle between two vectors, right? Sure, not well, not really, not really. Here's. I'm going to write something down which will hopefully jog your memory a little bit. Do you remember us saying that the cross product? Well, let me just cut to the chase. The cosine of theta, the angle between two vectors, right? And let me know if this even sounds familiar, is equal to the magnitude of the two vectors, right? So magnitude of A, the dot product, that is, of the two vectors, magnitude of B, divided by the, or the dot product, I should say. I shouldn't say the magnitude, the dot product of the two vectors. And then on the bottom of this, we're going to put the magnitude of the two vectors. In fact, I kind of messed that up. Let me erase that. So on the top, we said we're going to take the dot product of the two vectors, A dotted with B, and divide that by the magnitudes of the vectors. The product of the magnitudes of the vectors, that is. Does anybody even remember that? Does that even sound vaguely familiar to anybody? Right? Tan? Whoa! Where's tan coming from? No. We use sine for that. That's something we did yesterday, though, right? So let's go ahead and find the dot product of these two vectors. Now remember, dot product is easy. That's not the one that takes up all the time. Dot product is easy. So it's 3 times 2 plus 4 times 0 plus 5 times 2. What are you getting when you find that dot product? You tell me. What's the dot product of these two vectors? Come on, folks. Do it for yourself. What do you get as a dot product? All right, let me show the vectors again. 3, 4, 5, 2, 0, 2. What's that dot product? Don't wait for somebody else, folks. Work it out for yourself. Okay, there you go. 16. So 16 on top. Now we have to find the magnitudes of those two vectors. 3, 4, 5, excuse me, is the square root of. So remember, you can always find the angle between two vectors if you have the vectors, right? And the two square roots. So this would be the square root of, let's just see, 9 plus 16 plus 25. That's that square root. And the second one is going to be the square root of 4 plus 4. All right. So that is working out to be 16 over, I don't know. I need your help with this, folks. I need your help with this. Is it 50? So it's the square root of 50 is what you're saying? Is that what you're saying, square root of 50? Yeah? Okay. I'm going to take your word for it. Oh, is it for both of them or just for one? Because you can multiply the two together. Just for one. Okay. Dotted with the square root of 8 then, I guess. That shouldn't be too hard. So that's if essentially, by the way, it's equal to 16 over the square root of, I can do that. 50 times 8 would be 400. Well, that's actually 20. Okay. And that, of course, works out to be, what is that? No, 4 over 5. Okay. Does that make sense? 4 over 5? Just for, okay, good. So it turns out that theta is equal to cosine to the minus 1 of 4 over 5. Whatever that is, right? It's just going to be some number. I don't know what the number is. It's going to be some number. No, because these are and we can get that number. I'm going to show you something else that we could actually do to figure out what we're going to do with the cosine. But what is this angle? Give me the angle, please. Anybody? Give me to a couple of decimal places. What angle is this? 36.87. Okay, thank you. So now we can go back now and put that all together in this formula, right? Magnitude of A, magnitude of B, times the sine of that same angle, right? But what I would do is I would leave that number in the calculator, and we're going to take the magnitude of A, which we already figured out, by the way. Magnitude of A was the square root of 50. So square root of 50. So this is going to be, remember what we're doing is we're finding the magnitude of the cross product, right? That's what this number worked out to be, right? The magnitude of the cross product was 12. So we're trying to find the magnitude of the cross product again. Let me erase this. So there's the magnitude of the A crossed with the B, and we're saying that's equal to magnitude of A times the magnitude of B times the sine of the same angle, 36.87. Well, the magnitude of A we already figured out to be the square root of 50. So square root of 50 times the square root of 8 times this sine of whatever it is, 36.87. Now, because we rounded, you may not get it to be exactly 12 unless you kept the number in your calculator, right? So in fact, square root of 50 times 8, we already found it out as be square root of 500, of 400, which is, this just works out to be 20. I mean, let's just cut to the chase here, right? Square root of this just turned out to be 20. So it's going to be 20 times the sine of the 36.87. Okay, folks, what are you getting when you do that? Put that all together in your calculators now. Tell me what you're getting when you do that. Getting approximately 12. Now, again, we at some point may not have gotten this to be exact anymore because we're using this decimal thing, but the answer turned out to be 12. So there's your proof right there. All right. Okay, so one more thing I should mention, right? I don't have a slide for that, but I should mention that one of the things that you saw Mr. Richards do, and that's an important point, and maybe I should have put a slide together for that, is that when you, all right, let me quickly add a quick slide for that here. When you take two vectors and you find their cross products, so vector A, vector B, right? It turns out that the cross product of this, the magnitude of the cross product actually works out to be the area of the parallelogram that you would form between these two vectors. So if I were to finish this parallelogram, and that's a weird looking parallelogram. That's not even close to being a parallelogram. But anyway, the area of this the area of this parallelogram is actually the same as the magnitude of the cross product between A and B. That's an important point to remember. All right, so the magnitude of A cross with B is equal to the area of the parallelogram. I can't spell parallelogram properly. Area of the parallelogram that you form by filling out the rest of this. All right, so just an important point that came out of the video, which I didn't really address before, and it's something you do need to know. All right, so if I want to find the area of a parallelogram formed by putting these two vectors together, then I just simply find the cross product and find the magnitude of that cross product, and that represents the area of the parallelogram. Okay, all right, so as far as your success criteria, can find the cross product of two geometric vectors and its magnitude, cross product of two algebraic vectors, use the properties of cross products to find vector products. All right, okay, gonna move along. Let's hear any questions on that. I want to try to squeeze in today. It's what, 12:08 now? We're about 20 some minutes left. I'm going to see if I can, over the next day and today, the second half of this class, or what's left of the second half of this class, do something that's kind of familiar to you, but with a little different approach to it, which is to find the equation of a line in 2 space and in 3 space, right? You've done equations of lines before from grade 9, but we're going to take a vector approach to it. So I can find it quickly. Okay, hold on. Give me a second here, folks. Units 8, equations of lines and planes. There we go. And I know I'm throwing a lot at you in a short amount of time, but that's the nature of things. You have the video later that you can certainly go to kind of go over what we did. All right. We're going to develop a way to express equation of a line in 2 space based on vector concepts. So you've all done y equals mx plus b. That's not new to you. We're going to be able to express equation of a line in 2 space in vector and parametric form. All right. By the way, you have no homework tonight, but you certainly do need to turn in the homework from last night. Just reminding you of that. I expect that by the end of the day. All right. So in earlier math courses, you studied linear relations. All right. That's for back in grade 9. And one focus was the equation of a straight line, y equals mx plus b. Right. What are the factors that determine the units of the straight line? Well, there was the slope and there was the y-intercept. Right? You all remember that slope was the m and the y-intercept was the b. Right? So nothing, new there. That's stuff you did back in grade 9. Now, what if we try to put this in terms of position vectors? I'm going to remind you what a position vector is, first of all. If you look at this diagram here, position vectors are vectors that start at the origin and end up at some point in space. So here's P1, here's P2. These are 2 points in space, in a two-space diagram, that is, that originate from the origin and run from the origin to that point. That's what we call a position vector. And you can find, you can create a position vector from any point within a two-dimensional space, right? And you can sum those vectors together. We know we talk about the basis vectors as this sort of, the first, position vectors that you can use, and you can scale them and get any other vector. We talked about all of that before. Well, we're gonna denote the points on the line as being p, x, and y, and then each of the position vectors is going to be O to that point py. Now, in general terms, I'm just going to skip to the cut to the chase here. We can define the vector equation of a line as being some point on the line, x1, y1. So they give you any point, and it could be any point on the line. So you're going to give the coordinates of that point. And it's going to be, we're going to try to extend that to 3 space eventually as well. So this is how we define the equation of the line now. It is going to be 1 point on the line plus some scalar multiplied by a position vector, AB, right? I'll show you what that looks like in a second. So there's some position vector that you're scaling, right, with this t here, and you add that onto some other point on the line, right? So some arbitrary point that's on the line. What does that look like? Well, here we go. Line passes through 5 minus 3 and has a direction vector. It's actually called a direction. I shouldn't call it a position vector. It's called a direction vector when you're looking at writing these equations of lines. But it really is a position vector. Has a direction vector, as a direction defined by vector m, 3, 2. Okay? Write its vector equation. Determine whether the points 17, 5 and 4 minus 12 are on this line. Okay, so let me take you back to the first page again to show you the format. Xy equals, and you see there's a point on the line plus some parameter, which we're calling t, it's a scalar, times a direction vector. All right, so let's see if this can make sense now. Passes through that point, has a direction defined by the vector 3, 2. So it really looks like this. So it's the xy is equal to the point 5 minus 3 plus, and we'll use t. T is kind of, typical scalar that you use, plus t times 3 comma 2. So we're saying you can define any x and any y on this line by using a point on the line, which is the point that they're giving you, 5 minus 3, and some scalar multiplied by the direction vector 3, 2. So I know this doesn't sound anything like y equals mx plus b, right? But I devised it this way so that they could also extend this to 3 space, right? So in 3 space, we'll see how that equation is going to look differently. So write the vector equation, which we've just done, and determine whether the points 17, 5, and 4 minus 12 are on the line. Okay, so I want you to understand that what we're saying is that every x on this line would be 5 plus 3t, and every y on this line is going to be equal to minus 3 plus 2t. Just depends on the value of t. So I can generate any x and any y by just simply changing the value of t. If t is 1, that gives you a particular value of x. If t is 2, it gives you another value of x, and so on and so forth, right? So the question is, if these are the equations, well, first of all, the original equation is this here. That's the vector equation, right? They usually refer to these as the parametric equations, right? That I just wrote out. That the x here is equal to the 0.5 plus 3 times t, and the y here is equal to the minus 3 plus 2 times t. Well, let's find out if this 0.175 is on the line. Does it actually fall on the line? Well, what we're going to do is we're going to take, now remember, 17 is my x coordinate and 5 is my y coordinate. So if I set my x as being 17, right, using this formula here, x is equal to 5 plus 3t. So that means that 17 should be equal to 5 plus 3 times t, right? If I can solve that, then I can figure out what my t is. That could help me to find my corresponding y. So this is a very simple equation. So let's take the 5 from the two sides. So 12 is equal to 3t, and therefore t is equal to 4. So what we're saying is, well, since t is 4, that should tell me what my y value is, right? My y value should therefore, here's what the parametric equation for this says. Y is equal to minus 3 plus 2t. So my y value should be equal to minus 3 plus 2 times 4, right? Because for every corresponding x value, right, that gives me a t which is 4. So I need to use that same 4 to generate my corresponding y value. So minus 3 plus 2 times 4. So that should be minus 3 plus 8, which of course is equal to 5. So what does that tell you? 17, 5. This point is on the line, right? The line that's described using this vector format, xy, is this point with the scalar of this direction vector, right, does describe a line which does have this point of 17, 5 on it, right? What about the point, what about the other point? What about the point minus 4, 12? Is that also on the line? Well, let's find out. Let's go over here and try that out. So no, my x value, and by the way, I could have started off with the 5 first, just FYI. I could have put the 5 into the y, got my corresponding t, it would still be 4, and I would plug that 4 into the x equation, x parametric equation, and I would still generate the same value of 17 for my x, just doing it the other way around. Is minus 4, 12 on this line? Okay, so let's think this through now. Let's start with the minus 4. So minus 4 is equal to, excuse me, 5 plus 3t, right? So again, I'm just trying to figure out what t value I'm working with for the minus 4. Bring that over. So that would be minus 9 is equal to 3t. And therefore, t is equal to minus 3. All right, just solving a very simple equation. Putting that into the y, my y value should be equal to minus 3 plus 2 times minus 3, right? 2 times that same value of t. So my y should be equal to minus 3 minus 6, which of course is minus 9. So what is that telling me? Minus 4 minus 12 is not on the line. Because with that same parameter of t, I get different x and y values that I should get. So what this is telling you is that this is not on the line. So let me write that down. So minus 4 minus 12 is not on the line. Whereas the first one, which was 17.5, is on the line, defined by that vector equation. Okay, I just want to quickly check and make sure that that all made sense. Okay, Javier, how about you? Did that whole sort of logic make sense to you, Javier? What do you see about that? You're good with that? Okay, good, 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 good. So not talking y equals mx plus b again, right? We're talking about a vector version of the equation because now we're dealing with vectors. And again, this does extend to three space, which I'm hoping that we're going to be able to get to. So these equations can be rearranged in a way that isolates the x value and the y value, which we just did. And we call these the parametric equations of the line, right? So here's my, again, x and y equals the point plus the parameter multiplied by the direction vector. But as you just saw, so I'm going to write the equation of the line in parametric form. And we just did this. So, I mean, I'm kind of doing, again, what I just did a few minutes ago. The parametric form. So here are the parametric forms right here. And I just did this a while ago. So the first parametric equation is that x is equal to 4 minus 3t. And the y is equal to minus 5 plus 7t. There's your parametric form right there. Okay? All right. Find the vector and parametric equations of the line passing through 7 minus 2 and parallel to the line, and they give you a different equation of a line. So xy is equal to 2, 3, 1, minus 4. So what do you think then? All right? I need vector and parametric equations. They've given me one that's parallel to it. So what do you think I'm going to use when I'm writing this equation if it's parallel to another one that looks like this? Right? Can I get some feedback from you on that? Right? They gave you the point, but they didn't give you a direction vector. Right? The point is the 7 minus 2 point. What am I going to use as my direction vector though? What do you think, folks? What should my direction vector be? I'm asking the class now, folks. I'm asking you to chime in on that. What should my direction vector be? It's parallel to the one that's on the screen right now that I just underlined. So what should the direction vector be? I want to, folks, I need some reaction from you on that. What should my direction vector be? Parallel means what to you? They're running in the same direction, right? Yes or no? Does it mean they're running in the same direction? Yes, it does. So if I have a direction vector for this equation, shouldn't I just use the same direction vector for the new equation I'm going to write? Absolutely. That's all it is. Folks, don't overthink this. This is easier than you think. Here's my solution. My xy is equal to not 2, 3 anymore, because it doesn't pass, well, it might pass through 2, 3, we don't know. But the point that it does pass through is the 7 minus 2 plus the t times the direction vector that we had before, which is 1 minus 4. Right? If they're parallel, they have the same direction vector. Right? They just go through a different point. That's all we're saying. That's all we're saying. Right? Thank you. Thanks for reacting, by the way, Taj, Sarah, and Fernando. All right. So my next step now is to write the parametric equations. Well, this is easy now. This is so easy. So my x is equal to, well, come on, let me ask one of you. Come on, we've done this. I've done this 3 times now, right? Let's see. That was Kushi the last time. I'm just looking for some parametric equations here. And let me ask Taj. Taj, you're usually very vocal anyway, but give me your x parametric equation, please. Go ahead, Taj. 2. Except it's for the one that I wrote down. Remember, the one I just wrote down is the one that's on, it's that we're using right now. Okay? The one that they gave you is a different one. I'm using the one that I just wrote down. Find the vector and parametric where the line passing through that point, so 7 plus t. There you go. That's not I. That's not I. Hang on. Sorry. Seven plus t. Good. Okay, Taj. Well done. And all I'm looking for now, Taj result, is my other parametric equation. Right? And I'm going to go to Thomas for that. Thomas, first of all, check in and let me know what that is, please. Thomas, your time. Are you there, Thomas? Hello, Thomas. Looking for Thomas. Where is Thomas? Great. Okay. So let me show you what Taj just did and what I've been doing all along. Let me take you back. And it's okay to be confused, right? So I'm fine with that. So when we were doing this equation, so I'm going to point to this one now, xy is equal to 4. You have a point on the line plus some parameter, which is like a scalar, multiplied by what's called a direction vector, the minus 3, 7. So to get the x, watch what I'm going to do. To get the x, I'm going to take this number plus this number times t. So that's why I got the 4 minus 3t from. You see what I just did there, Thomas, to get the first one, the 4 minus 3t? Good. To get the y, I'm going to use green now. I take that number, and then this number times this times that. So I get the minus 5 plus 7t from that. You see that? Does that make sense? All right, sorry about the color scheme. Okay, all right, so let's try that. And let me show you what Taj just did. Taj gave me the x parametric equation, which is the x is equal to the 7 plus 1t, or just 7 plus t. I'm looking for the y parametric equation now, please. The y parametric equation. So y equals, go ahead, please. That's why it's so important for me to call on people individually, because I want to be able to clear up any of these confusions, right? It's that to me is important, because like I keep saying, I don't leave anybody behind. I want everybody to be there with me as I go through this. Why did we ignore the 2, 3? Because, okay, Kushi, thanks for the question. We're not looking at this equation anymore, right? This equation says we want to find a new vector equation and parametric equations. That line is passing through this point, right? So we're going to change the 2, 3, right? Because that 2, 3 represents the point that the line goes through. It's parallel to that line. So what we're going to focus on is using the same direction vector. The direction vector is the what? It's like the slope. It's like the slope equation. It's like the slope. It's like the f. It's really what it is, right? Yes, it is parallel, Fernando, right? So we're finding the parametric equation for the one in red. He wrote, I got confused too. Oh, no, we're not. No, yes, I know. I realized that, Tash, from your answer before. We're not using this anymore because here's what the question says. Let's go back and look at the question. The question says to find a vector in parametric equation, the line passing through this point and parallel to this line. And that's why this equation that I wrote down is the equation that we should be focusing on. Okay, so Thomas now has an answer. He has minus 2 minus absolutely. Let me go back to red. So it's minus 2 minus 4t. So that represents the first one underlined in green is my vector equation. And the ones that are under that would be my parameter. Do we have t factor 2 as our final answer? Do we have a t factor? Oh, it's I see what you're saying. In that case, yeah, I guess it's better to write it that way. For parametric equations, I understand what you're saying. To factor out the minus 2, it isn't always possible to factor anyway, so it's probably best just to leave it the way it is. All right, I get what you're saying though, Fernando. All right, so thank you, Thomas. Well done. All right, let's see how much we can squeeze in the 7 minutes that we have left here. All right. Find a vector and parametric equation for the line passing through minus 1, 3 and perpendicular, and perpendicular to the line. And now these lines are expressed in parametric form, right? X equals 5 minus 2t and y equals minus 4 plus 3t. Ouch. Well, let's do this. Before we panic, let's see if perhaps we can put this equation, right? These are parametric equations. If we could put it into vector format, right? What's the point, right? Plus t times something else. Can anybody, I'll take a volunteer on that. Can anybody help me to put it, okay, we know it's xy. Let's do that part first. So that part is pretty clear, hopefully. What would I put as my point, and what would I put as my direction vector? Can somebody sort of walk it back the other way now and tell us what this is going to look like? And I'll take a volunteer on this one. I'm not gonna spin the wheel on this one. All right. What would be the point and what would be the direction vector? So 5 minus 4 is the point. That's correct. Right? And what do you think is a direction vector on that? The minus 2, 3, absolutely. Okay. So that would be, excuse me, that would be the direction vector. No, we want something that's perpendicular though. Now, here's what I want to say to you. I want you to think of, go back to grade 9 for a bit. One of the things that you'd have learned back in grade 9 is how do you find the slope of a perpendicular line? Remember that? What was that two-word phrase that you were taught? Look at Richard. Nice. Negative reciprocal. So how do we find that negative reciprocal again? We would normally flip the thing over and change the sign, is what we would do. If you haven't figured it out yet, this direction vector is roughly the slope of the line. It's really what it is. So in a sense, what you want to try to do is you want to try to find another vector, right? Another direction vector that would do exactly what that negative reciprocal would do that Richard just talked about, and give you a vector, direction vector, which is at right angles to the direction vector that we have right now. Can anybody think of what that direction vector might be? So the direction vector we have now is minus 2, 3. Do you think you could figure out a direction vector that would be at right angles to that direction vector right now? Can anybody come up with a vector, right? This part here, which would give us anybody. I'm not calling anybody in particular. I'm just trying to see if anybody can come up with something that they think might give us the perpendicular direction vector at right angles to it. Nobody thinks they know? 1 over 2 and Fernando is the closest, but not actually no, that's not quite true. No. Richard is except Richard, remember that negative reciprocal means you also change the sign. So maybe instead of it being 3 minus 2, maybe it should be just 3, 2. No. Here's what, no. And there's a way that we can prove it, by the way. I'm going to say it, and then I'm going to let you sort of figure this out. I'm going to say that it's actually 3, 2, right? Here's one way that I can prove to you that this direction vector is perpendicular to the one that we just had. Let's dot these two together. Why am I saying that? Because the dot product of two vectors that are perpendicular is 0. Right? Isn't that true? We learned this yesterday, and in fact, I showed that to you earlier on today. What is the dot product of these two vectors right now? It's going to be 3 times minus 2 plus 2 times 3. Well, in my world, that's minus 6 plus 6. If I can find two numbers, and usually what it is just simply trying to get, and the easiest way to do this is to do this. Put the 3 over the 2, over the minus 2. Flip it over, change the sign, and then use that to get the vector. So in a sense, it's just like when you were doing the direction vector, the negative reciprocal from back in grade 9, right? So I'm going to say to you that the direction vector that we need right now is a 3, 2 direction vector. Not negative 3, but positive 3. So you're not just changing the places as you did, Richard, but if that ratio that you had was negative, you want the ratio now to be positive, is what we're saying, right? So you're going to flip them around, but you're going to change whatever the ratio is before. The ratio now is a negative ratio. Change that to a positive ratio. So I'm going to go ahead and let me erase all of this here. I know we're almost out of time. I know. I'm quite aware of that, folks. Right? So I'm going to say that I'm just going to give the answer. And we'll talk about it some more tomorrow. It passes through the point minus 1, 3. and has a direction vector of 3, 2, right? Because it's perpendicular to that line. All right.